you can see there. So it is indeed a very hard task to do. So it's clear that from amplitudes it is not going to work. So we have to do something more. We have to develop some features that extract better information. We will consider here 3 types of features. So wavelet coefficients. Remember, we introduced wavelet scalograms when doing spike detection. So can we also do that here to construct a wavelet scalogram? We will look at phase synchrony and wave propagation. These terms will become this become clear in a moment. I'm now on slide 46, wavelet transformation. So you see 2 electrodes here, electrode 28 and electrode 80. And you see this is the averaged case for a lot of trials of a particular day. And with a model wavelet DB7, so WBC7, you see the wavelet scalogram. Vertical axis show you the scale. So these are actually frequencies, right, from low to high frequency. And on the horizontal axis, you have the time axis. This is the time elapsed after stimulus onset. And this is the difference taken between rewarded and non-rewarded stimuli. So everything in red, it means that there you have more activity for the rewarded case. And if you see the blue thingies, that's the opposite case, where the unrewarded one is more active. And you can see from an eye blink here that there is difference here. There is structure between red and blue. And what you also see that picture is different for electrode 80. So it depends on which electrode, how the picture will look, but you see that in principle something is feasible. The little blue red squares are the ones that were taken after a t-statistic analysis. We'll come back to that later. Now we're going to slide 47, phase synchronization. So the wavelets is one. Another thing is looking at the phase. Another feature we will extract here, and we are actually considering here some important statements about phase. You can have actually 2 oscillators that are coupled, but the amplitudes are uncorrelated, and even in that case, they can be in synchrony. And that's, of course, a very weird case. It comes from chaos theory, where you have all sorts of weird oscillators with properties. And if you would use coherence, which is a very popular strategy, a very popular metric used in brain recordings, to model brain recordings, but this coherence is actually a correlation, but in a spectral domain. And of course, if you only consider the amplitude there, you get actually a confusion between amplitude and phase in the relation between the signals you're looking at. Remember, if you compute the amplitude, for example, from a signal that is in essence complex valued, that it has a real imaginary part, it has also a phase in there. If you're gobbling this way amplitude and phase, you will not be able to resolve it, and you can actually miss out on the phase synchrony that is underlying the connection between the two oscillators. So, well, what is phase synchrony? You actually computing the phase of one signal, and you have the phase of another signal, and you look at the case where these 2 phases, phase evolutions, are, when you subtract them, are within some threshold, some constant. And if that is the case, that there is phase locking. Of course, as you see in a moment, the phase of a brain signal is increasing all the time. So it means you will cross the phase circle. It goes from 0 to 2 pi, and then to 4 pi, and 6 pi, and 8 pi. So it continues all the time. So in order to account for that, you can do everything modulo 2 pi. I'm now on slide 49. So you extract the phase in different ways. You can do it. The most A popular one that we also use is the Hilbert transform. It's a particular transformation that mathematical construct that extracts from a real valued signal a complex valued signal, and if you have that, you can take the ratio and compute the phase. This is something we have discussed in one of our first chapters, where we introduced some concepts about signal processing. The second is a wavelet transform, the so-called complex wavelet, which is actually looking at the sine and cosine at the same time, and this way you can also extract by taking the ratio the phase from your signal. So anyway, whatever method you are applying here, you can extract the phase. So by the fact that you have a complex valued signal now. So this on slide 50, you see an example of local field potential with all the wiggles. And on the right panel, you see the phase that is extracted. And here I draw your attention to the vertical scale. It's in 2 pi, as you go from 0 to 1, 2, 3, 4, 5, 6, and so on. You see that the phase is continuing to increase. And this is what I just said. Okay, then they are now on slide 51. You can use the phase as it is, but actually that's not what people do. It's a bit, not so stable, let me put it this way. I mean, you're looking at biological signals, so brain signals are notoriously complex, notoriously difficult to work with. So people are using other metrics, and a few of them are listed there. I'll not go through them. Maybe the last one is actually plotting all your phases in sort of histogram. And if that histogram is pretty flat, then you have maximum entropy of that histogram. If that histogram is peaked, meaning that the phase difference is really restricted, then you have low entropy. So this is what Tas and co-workers introduced as a metric of phase difference, but then expressed in terms of an entropy value. You can use other techniques. We have been using mutual information, which is a nonlinear way of taking correlations between two signals, in this case, two phase signals. Okay. Now on slide 52, here you see a rendition of the Utah array. All the black dots in that square are indicating electrodes. We have actually 10 by 10, so it's 100 electrodes. You see some white circles there. 4 of those are not wired, and that's indicated by these circles. As I said before, only 96 electrodes out of 100 are wired in case of the Utah array. Okay, 4 panels are shown. They show the synchrony level in day 37. So for monkey 1, this is the day before the switch, where we switch the paradigm. Remember, the rewarded becomes the unrewarded one. And there you see, if you take the difference between rewarded and unrewarded, the panel top right, you see some structure there close to the border, some structure that is significant and different. So there's a significant difference in synchrony level between the rewarded and unrewarded case. If you go to the next slide, there we see the effect as a function of learning. So the first day, learning day 1, there was nothing at all to be noticed here between the rewarded and unrewarded stimuli. There was no difference in synchrony, but on day 37, the top right plot, you see the difference. And then suddenly, one day after the switch, the reversal of the rewarded stimulus, you see immediately everything turning blue. So what was yellow and red becomes now blue and dark blue. So this is as expected. The monkey doesn't know that the thing has been switched. And after some continued training, so after reversal day 20, you see that everything has been restituted. That corresponds now to what we had in day 37. So the monkey has indeed remapped it and learned that the paradigm had changed. Okay, so then slide 54, you see how the time course over training days is. You see here also